Hello everyone and welcome to this tutorial on quantifying uncertainty in machine learning assisted measurements. My name is Shervin Shir Mohammadi. I'm a professor from the University of Ottawa in Canada. As we all know, machine learning is now extensively used in all technical and non-technical fields, including measurement. And like any other measurement, it's very important to quantify the uncertainty introduced by machine learning so that the resulting system can be deployed in the real world, it's trustworthy, and it has a good performance. So in this tutorial, we're going to look at how machine learning is used in measurement. We're going to very briefly look at uncertainty and then how machine learning contributes to measurement uncertainty. Then we are going to look at measurement scales that impact machine learning regression and machine learning classification differently. And finally, once we have all of that knowledge, we are going to look at how we can quantify the uncertainty of machine learning regression and machine learning classification. Before I get to the technical part, I just want to make two quick notes. One is that this tutorial has a corresponding article in the Instrumentation and Measurement magazine, and I encourage you to read that for more details. And the second note is that because of shortage of time, I'll be going too fast maybe on some slides. By all means, do feel free to pause the video to more carefully see the content. This is especially important for people who want to write the quiz afterwards. And also on some slides, I'm citing references. By all means, go and see those references if you need more information on the topics of that slide. So with that in mind, let us take a look at how machine learning is used in measurement. Essentially, it is used for indirect measurement. In this diagram, I'm showing that I want to measure Y. Maybe I can do that directly. But sometimes I cannot directly measure Y because it's too difficult, it is maybe too expensive, or maybe does not meet timeliness requirements, or many other reasons. In those cases, I may be able to measure directly some other quantities like x1, x2, x3 in this example. And if I know the functional relationship f between those x's and the y, then I have indirectly measured y, because y is equal to f of x1, x2, x3. And if I represent x1, x2, x3 as just simply the vector x, then I simply have y is equal to f of x. Now the question is, how do we determine this f? There are two general approaches for that. One is by analytical modeling, which is done by a domain expert who uses the laws of physics, biology, chemistry, mathematics in order to develop a model, analytical model for f. And the other approach is data-driven modeling. If we have a data set with a large number of x's and y's that we have already measured, then we can use data-driven modeling to determine f. And one of the most common approaches to do that today is with machine learning. So in machine learning, we use the data set, we train the machine learning model, and the outcome will be a hypothesis or an estimator, which we call f hat. And this f hat is basically an estimation of the f. Now, because it's an estimation and not necessarily exactly f, there's going to be some uncertainties already here, as you can see. So let's take a look at uncertainties. What is measurement uncertainty? According to the ISO GUM definition, uncertainty is a parameter associated with the result of a measurement that characterizes the dispersion of the values that could reasonably be attributed to the measurement. So in this diagram I'm showing here, for example, you can see that we have made repeated observations. And each observation is slightly different because of systematic effects and because of random effects that affect the measurement. So each time we get a slightly different answer. And that difference essentially is what uncertainty is trying to characterize. So this dispersion between these values is what uncertainty is trying to characterize. The standard gives us two evaluation methods, type A and type B. If we have already made a number of observations, so more than just one observation, then we can use type A evaluation method, which says that the type A standard uncertainty is basically the experimental standard deviation of the mean. And that's it, that's our type A standard uncertainty. But if we cannot make multiple observations for whatever reason, then the standard tells us to use the type B evaluation method, where we use things like previous measurement data, manufacturer specification, and some other information in order to be able to quantify the uncertainty. So for more about uncertainty, I strongly recommend the tutorial of my colleague, Professor Alessandro Ferrero from the Polytechnic University of Milan in Italy. He has both a video on YouTube and a very accessible article in the IEEE Instrumentation Measurement magazine about uncertainty. Okay, so generally speaking, uncertainty is important. And the importance is even magnified in machine learning assisted measurements because of a number of reasons. First of all, as you noticed, the f hat that I showed you actually estimates f. So already there is some uncertainty that builds up there. Secondly, today, most machine learning approaches are based on neural networks. And neural networks are today, unfortunately, are overconfident. If you look at this diagram, you can see that in the 1990s, the average confidence of a neural network was slightly lower than its accuracy, which is good. We want to be on the safe side. But today, unfortunately, the average confidence of a neural network is much higher than its accuracy. And this leads to practical problems because the neural network will confidently, very confidently give a very wrong answer to the user, and the user will lose trust in the system after a while. So what can be done about that? Studies have shown that, in fact, uncertainty can be used to predict this misclassification. So if we determine the uncertainty and we see that the uncertainty is high, we can inform the user that this, although the neural network is confident, the uncertainty with this measurement is high. And either the user can do something about it, or the model can be retrained, or other approaches can be taken. But what is important is to determine the uncertainty in that instance. How does machine learning contribute to the measurement uncertainty? Let's take a look at a full cycle of a machine learning based measurement system. Here we can see that we collect a data set, and this data set actually comes from measurements because the data are collected from sensors or other sources, and those equipment are essentially doing measurements. So because there are measurements, there is noise and bias in the measurements because they're impacted by the random effects and systematic effects. So already the data set has some uncertainty. Even if we eliminate systematic effect as much as possible, which we are required to do by the standard, there is at least the random effects, which we cannot always completely eliminate. So the data set already contains some uncertainty. And in machine learning terms, that's known as the aleatoric uncertainty. Now, this data set is used to train a machine learning model, which is essentially comes up with an f hat that estimates the functional relationship. Because it is an estimate and not necessarily exact, this also introduces some uncertainty. And in machine learning terms, that's known as the epistemic uncertainty. Here I'm showing a diagram of how that plays out. So here the black dots are my data set, which you can see are exactly the same in all three diagrams. The blue line is the f hat, and here you can see that f hat is doing a very bad job, obviously. So we say in this case the model underfits and it's biased. The other end of the spectrum, we can see that here f hat is matching the points too closely. It's not only matching the points, but it's also matching the noise in it, which we don't want. So in this case, we say that the model is overfit and has a high variance. What we want is something like this, which hopefully will be generalizable. Okay, so now we know how machine learning is used in measurement and how it produces uncertainty. Now, how can we quantify that uncertainty? Before we can answer that question, we have to look at measurement scales, because machine learning is in two categories. One is machine learning classification, and the other one is machine learning regression. And each of them operates in a different measurement scale. So let's take a look at these classification and regression first. Here is an example of a regression. Here the x-axis is the amount of pesticide and the y-axis is the number of disease plants per hectare. So this is regression essentially, but machine learning here is trying to determine the f hat, and the f hat is predicting a continuous quantity. Classification, on the other hand, you can see in this example, is concerned with classifying the input into specific classes, class labels, we can say. So here you can see that there are two tests, test 1 and test 2, that are being done on a product, and based on that, the quality of the product can be determined to be either 1, which is the lowest quality, or 2 or 3, or 4, which is the highest quality. And these are field tests that we have collected in our data set, and the machine learning classification model here has come up with these dashed lines, which are the decision boundaries. And now if we give a test 1 score and a test 2 score to this model, it'll predict for us what is the quality of this product. And you can already see that at the boundaries especially, there is also quite a bit of uncertainty. So these are the different types of machine learning approaches, and they relate to measurement scales in the sense that, as we know, there are these measurement scales: nominal, ordinal, interval, ratio, and absolute. And if we look at machine learning classification, that operates in the nominal and ordinal scales where there is no units. So here values don't have units. Whereas machine learning regression operates in the interval, ratio, and absolute scales, which do have units. Now, this is very important because the standards give us uncertainty quantification methods for the last 3 measurement scales, but not for the first 2. So there are no standard methods for determining or quantifying uncertainty in the nominal and ordinal scales, and we're going to see how researchers have handled that. So let's take a look first at interval, ratio, and absolute scales, or in other words, machine learning regression. Here we can use the existing standards. It's not too big of a deal. We just need to do a little bit of work that I'm going to show you. So let's say we want to do type A uncertainty evaluation for a machine learning regression system. What we need are multiple observations, but of course the machine learning function f hat is deterministic, so whatever input you put into it, it always gives you the same output for that same input. It doesn't change. How can we get around that if we want multiple observations? We can use methods such as Monte Carlo dropout, Monte Carlo batch normalization, deep ensembles, dropout ensembles, Bayesian neural networks when approximated by dropout, and some other methods. Let's take a look at one of the Monte Carlo dropout first. So here what we do is, let's assume that our machine learning model is a neural network as shown here. Again, if you give it x0 and x1, it always gives you the same output y, but we want different observations. So what we do in Monte Carlo dropout is that we insert these dropout matrices Z1 and Z2 that have values that are sampled from a Bernoulli distribution. And then we give the same input to the model multiple times. Each time, this model is going to drop randomly 1 or more of the neurons, or maybe 0. And because of that, we are going to get slightly different answers for the same input each time. Okay, so now we have the multiple observations. From now on, it's easy. We just use the existing standard type A evaluation method. So in this example, let's say we have done Monte Carlo dropout and we have come up with these 5 different temperature values according to the type A method. Here, the uncertainty is 0.09 degrees Celsius, and because the average is 72.84 degrees Celsius, we can say the temperature in this case is 72.84 plus or minus 0.09 degrees Celsius with 68.27% confidence interval. So we can use the existing method here. Now, what if we have a model, a machine learning model, that doesn't produce a fixed output for the same input, but it gives us a distribution? Such models actually exist, such as artificial neural network with uncertainty output, or Bayesian neural networks in their pure form. Let's take a look at one of them. You see an example that the authors have used, instead of mean square error for a loss function, the authors have used a negative log likelihood loss. And as a result, instead of getting a fixed output, as we can see here, they are actually getting a distribution. So whenever you input something into this neural network, it doesn't give you a single value, it actually gives you a distribution. So then we can apply type B uncertainty methods in order to determine the quantity. Here is an example from the literature where someone has actually used this in order to quantify the uncertainty of the relative geometry in inertial sensor array. So this is an inertial sensor array. These are IMO units, inertial measurement units. The first one is taken as a reference, and for the others, they have used Monte Carlo and Bayesian estimation. in order to determine the uncertainty of the relative position of that IMU compared to the reference IMU. So the ovals that you see here, the red one, the green one, and the blue one, which is too small, these are the 50% confidence lines that have been collected for 550 and 500 time samples. So you can see that obviously the more samples we have, the less uncertainty there is in where the position of this IMO actually is. Okay, so for machine learning regression, there is no problem. We can use existing standards. What about machine learning classification, which operates in the nominal and ordinal scale? Well, there is no standard for ordinal and nominal scale for the uncertainty quantification. In fact, even for ordinal quantities, which officially fall under measurement, we don't have a standard, let alone nominal properties, which officially are not considered measurement according to VIM, although some standards refer to them as examinations. In any case, what people have done in practice to get around that problem is use different methods to quantify the uncertainty. So these are not standard methods, but they are existing methods. For example, Shannon's information entropy, deviation of predicted probabilities, cardinality of the results set compared to that of the reference set, and some other methods. You can read them in these papers and more. Let's just take a look at the first two, because those two are the most widely used methods in the literature. So let's say that we have this machine learning classification model that, given an image, it'll tell you if it's a cat or a dog or a cow or a duck. And in this specific scenario, in the first observation, it has determined that the image is 80% cat, maybe 15% it's a dog, maybe 5% it's a cow, and definitely it's not a duck. So this is first observation. And then we use Monte Carlo to generate the second observation, third observation, and fourth observation. So each time the percentages vary. And then we take the average here. And the result is that probably it's a cat, because that has the highest percentage, 78.5%. 16.5% that it could be a dog, 3.75% that it could be a cow, and 1.25% that it could be a duck. So that's our model 1. And you can see that it has not eliminated any of the classes. So please keep that in mind. We will get back to that later. Model 2 uses a different neural network and also does the same thing. So it has multiple observations. But model 2 has eliminated dog and duck, as you can see here. And again, the winner here is also cat, 79.75% cat. So let's use information entropy to measure the to quantify the uncertainty of these models. Here, uncertainty simply is the entropy, which is essentially you take the probability of each class, you multiply it by the log of that probability, and you add up over all classes, and finally multiply by -1. So for the previous two models, the uncertainty of model 1, if we do the calculation, it becomes 0.96, and for model 2, it becomes 0.73. Model 1 is highly uncertain because it has not eliminated any of the classes, and model 2 is less uncertain because it has eliminated 2 of the classes. So that's information entropy. Now, in an actual application, the designer has to come up with what is the threshold that says uncertainty is high or low. So that's application specific. These numbers by themselves don't mean anything, but they can be compared to each other, and also for a specific application, we can determine what is the threshold where uncertainty is high for that application. The other method, deviation of predicted probabilities. Here we can quantify the uncertainty as the standard deviation of the predicted probabilities of the predicted class. So in our case, the cat class won in both cases. So let's go here. These are the predictive probabilities for cat, 80%, 75%, 77%, 82%. And essentially this is telling us the standard deviation of between those values is the uncertainty. And if we do that in our example, for model 1, we get an uncertainty of 0.027, and for model 2, we get an uncertainty of 0.019. Some other researchers, they say we should use the standard deviation of not just the predicted probability of the predicted class, but of all classes. So in this case, we do the same thing, but over all classes, and we take the average. If we do that, then in our example, we get model 1 uncertainty is 0.98, and the uncertainty model 2 is 0.038. Here are two examples with which I want to wrap up the tutorial. Here is a vision-based classification example. Here you can see the dash cam of a autonomous car, and here is the actual scene, and here is the ground truth. This is done manually, so the purple is the road, the pink is the road, the purple are the cars, sidewalks are blue, buildings are red, and so on and so forth. So this is done manually. And the prediction frame here, this is what the machine learning model has classified for us. Now, if we look only at the prediction, you can see that it has mistakenly identified this portion as being road, but actually some of it, which is here, is sidewalk. It's not road. And also here it has been determined as being sidewalk, but this is actually road if we look at the ground truth. So this is very dangerous, because if the car is relying on this image to drive, and if the car wants to turn left, there is a danger that it actually runs over the sidewalk and maybe hit a pedestrian, which is what we don't want. If we look at the uncertainties, so aleatoric and epistemic uncertainties, we can see that the epistemic uncertainty is telling us that this region is actually highly uncertain. So in this case, the car is not going to look just at the prediction, it's also going to look at the epistemic uncertainty and say, oh, okay, uncertainty is high, so either I will not go left, I will go straight and find another way, or I will give control over to the human driver and say, sorry, I cannot drive here, please drive. So the decision has to be made here. So this is the advantage of having the uncertainty. Here is another example, which is an active daily living recognition system. It is trained with certain people, and then it is given to new people, and the idea is that this system can determine what the person is doing in their active daily living. It's a variable motion sensor, basically. And what they have done, which is interesting, is that not only they classify what the person is doing, but they also estimate the uncertainty. If the uncertainty is high, then they actually prompt the user, we think you are sitting, is that correct or not? And then the user can say whether it's correct or not. And the system can use that as feedback, hence active learning, to improve its model. If the uncertainty is low, then it just classifies it and assumes that there is no problem with the classification. So in this sense, the system over time can improve its performance and also at the same time customize itself to the individual. So just to wrap it up, the main takeaways are the fact that when we are working with machine learning, it is important to consider measurement fundamentals, especially uncertainty. This is starting to become well known, and fortunately, people are starting to look into that. Without taking uncertainty into account, our systems are not going to be trustworthy and will have limited practical application in the real world. So it's very important to have the uncertainty quantified. If we are using an ML regression assisted measurement, then we can use the standards, existing standards, to quantify the uncertainty. But if you're using ML classification assisted measurements, then we have to use other methods as I showed you. Thank you very much, and I hope you enjoyed this tutorial.